So the topic is horizontal dilation. And for an example, we're just going to look at a somewhat simple parent function. We're going to look at the function x squared. We're going to compare that to a fairly simple dilation. We're going to dilate that as an x over 2 squared. And before we actually look at the curves those generate, the first thing I'd like to do is expand out the t-table and take a look at the points each of these is going to generate. So we're going to take a nice big span. We'll start at -4 for our first t-table, and we'll just go in increments of 1. All the way up to 4. And we see the set of points that generates at -4, starting with a y value of 16, dropping down to 0 and back up to a positive 16. That's the parabola we're used to seeing, and we'll fill in the curve that generates with the purple ink there. And we're going to compare that then to the x over 2 squared. Again, we'll take a look at the t-table that generates before we fill in the spaces. Now I'm going to start at a -8 for my first x value, and you'll see why in a minute. And then we'll proceed only taking the even values for x as we go up through a positive 8. We see the black dots now that t-table generates from an x equals -8 for a y of 16, continuing down through the vertex and back up to a wider, now dilated in the horizontal axis graph of the curve x over 2 quantity squared. Now, why is that dilation factor of 2 in the denominator, which normally fractions make things smaller, right? That would be kind of the intuition that a lot of our brains like to gravitate towards. But I want you to think of it this way. When I'm putting an x value into this second dilated function compared to the parent, it takes twice as much x to get the same y that I got out of that first parent function, out of x squared. So if I take, for example, at x equals 2, for that second function, it took twice as much to get the output of 1 as my parent function required. So the parent function only required an x value of 1 to get a 1 for the output. The secondary, the dilated function, where I divided x by 2, or by the dilation factor of 2, it now requires twice as much x. So it requires a value of 2 to get that same y value of 1. And we can see that expressed all the way throughout the curve.